That's what you are, you're my limelight. I'ma show you off, make you shine right. Making sure you knowing that you're my life.
Welcome to the Grok Shop and part 3 in my series on converting this 36 volt golf cart to 48 volts. In this video, I'll be dealing with the state of charge meter. I'm going to show how to convert that state of charge meter from 36 volts to 48 volts, thereby preventing you from having to buy a new one. So one thing we'll need to know is the internal resistance of the state of charge meter. To figure that out, we'll just measure the current when the state of charge meter is hooked up to the 48 volt pack. And to do that, just break the circuit, put your multimeter in amp mode, and put it in the circuit on either the positive or negative lead. It doesn't matter. You can see here I've measured it out at 10 milliamps. Okay, so if any of you are electrical engineers, you may already be familiar with this concept. If not, trust me, you don't need to be an electrical engineer to understand this. Basically, if you understand proportionality and a little bit of algebra, you're good to go. So let's take a look at this circuit here. In relation to the state of charge meter, what we had to start with was 36 volts at V out, and then the resistance of the state of charge meter. And so this would be the circuit before the upgrade. In order to upgrade it, increase the voltage to 48 volts, we need to put a resistor in line. And the reason this works is because the voltage drop for the total circuit is proportional across each resistor in the circuit. So in other words, if R1 equals R2, then half the voltage will drop across R1 and half will go across R2. And the proportionality is linear. So since the voltage scales in a linear fashion according to these resistors, we should be able to use that ratio to our advantage. And so the whole voltage divider thing is built on that. And you can see the basic math here. The ratio of the output to the input is directly proportional to the resistor values. Okay, and so it's pretty much a manipulation of this formula here that lets us arrive at the needed resistance. So in order to get it though, we have to understand all these values. We know V out was 36, we know V in is 48. R2 is the internal resistance of the state of charge meter. We don't know that to start with. And R1 is the new resistor value, and that's really what we're looking for. So we just really need to figure out R2, and that's what I did over here with this state of charge meter internal resistance. So I just use Ohm's law, and I take a measurement. If you looked at that first part of the video before this slide, you'll see it came out to be 0.01 amps, which is the same as 10 milliamps. So we divide the applied voltage by the current, and we get the internal resistance, 4,800 ohms. Now, a lot of variables come into play here, and it's not going to necessarily be a continuous 10 milliamps, but it's just a ballpark figure to get us close. And trust me, it really doesn't make much difference. It all comes out in the wash. So I calculated it as 4,800 ohms, and knowing this, we can arrive at what we need to know. So here I've done the algebra to sort out R1. I'll save that as an exercise for your homework. But it works out to be R2 times V in divided by V out less the value of R2. Okay, and of course V out should not be 0. Okay, now plugging in the values we know, 4,800 ohms for R2, input 48, output 36, and R2 48 again, 4,800, I'm sorry. Doing the math gives us a desired R1 of 1,600. So if I place a 1,600 ohm resistor between the 48 volt supply and the input to the state of charge meter, I should get a state of charge reading that reads as if it's still reading across 36 volts. But because of the proportionality, it'll go up and down. So in other words, when this is 48, it'll show a full 36, and when this is down to like say 45, you're probably going to show 34 here. something like that, and so the meter will go down according to a proportion, in a proportional manner. So that does it for today's engineering and math lesson. I hope that made sense and that you're still awake. So if you have no resistor at all, you'll see the state of charge meter just be pegged off the chart. So we know we need a 1.6 k ohm resistor. I went through my box, I found a 1.8 kilo ohm, so that's close enough for me. But if I had a 1.6, I would use that. Of course, you could also use a pot. Be aware of the power rating for the resistors. This is a pretty small current level, but here's the power calculation. I've got 0.18 watts, so a quarter watt resistor would be fine. A 1/8 watt could get pretty hot.
So now, what about sockets? What about the sockets?
What about the sockets?
I don't see any more sockets.
You don't?
Nope. So I see some socket.
So with the resistor in the circuit, you can see where it hits on a 48 volt full pack charge. Just manually connecting it at this point. So what I'm going to do is solder on a ring terminal directly to the resistor and use that to connect directly to the positive battery connection. I just take a little wire from that terminal and wrap it right around the end of the resistor, and I'm going to solder it on here. When I solder, I like to use a non-conductive surface. Like here I have a piece of wood. Usually use a brick or a piece of tile or something so that you don't lose heat when you're soldering. So this is the wire coming from the state of charge meter. Just going to show how I use a cross twist technique to get a good tight fit before I solder here. Always try to make both leads the same length, whether it's wire, resistor, another wire, or what. Then that way when you cross twist it, everything works out perfect. So by cross twist, what I mean is just make a plus sign or an X, and each lead gets wrapped around the other lead. Makes for a very tight connection, good soldering, and also heat shrink goes on very well. And then before I go to solder, I want to crimp down on any edges that might be sticking out, so it's a nice tight cylinder and the heat shrink goes on smooth. And there you have it. That's how it's done. Thanks for watching.